And I'm going to insert a page here. Chapter 11, we're going to be comparing means of many independent samples. All right. So it says in chapter 7, we looked at the hypothesis test where we compared two samples, right? Mu1 equals mu2 was that hypothesis test, and it was the two sample t-test, right? We had two independent groups in our data sets, and then we went through that hypothesis test. This is not skipping over stuff. There we go. All right, so we had two independent samples or two independent groups, and we wanted to draw conclusions and compare them to see if their population means were equal or not, right? And so in this chapter, we're going to have I groups, and this is an I in italics. Sometimes it looks like a 1, so I'm going to put the little things here. But it's I, which is always going to be the number of groups. And so now what we're going to do is we're going to test the hypothesis that mu1 equals mu2, and up to however many groups that we have given by I, right? So if we have 3 groups, I'm going to have mu1 equals mu2 equals mu3, so on and so forth. All right? And so I have this example here. It says the table below shows the weight gains in 2 weeks of young lambs on 3 different diets, right? So we have diet 1, diet 2, diet 3. So we have a grouping variable, which is type of diet, and we're just giving the number of the diet. And then we measure the weight gain of the individual lambs, right? So on diet 1, we have 3 lambs. That means our sample size in this group equals 3. And since they call that diet 1, I'm going to use N with a subscript to notate the group. That size is 3. There are 5 lambs in that second group, so N sub 2 equals 5. And then there's 4 here. N sub 3 equals 4. And we have the actual quantitative variables values for each of those lambs. Now, it says if our goal is to compare the mean weight gain of lambs on the 3 diets, how can we use the 2 sample t-test to help us get there? Okay? How can we use this 2 sample t-test to determine if the means are different? Even though we have 3 groups instead of 2. What would we do? Any ideas? Grant, any ideas? No ideas? Well, there's 2 groups, right? 3 groups here, right? 1, 2, and 3. If I wanted to use 2 sample t-tests and I wanted to compare the group means, then what I would have to do is do multiple t-tests, right? I would have to do a t-test to compare the mean of population 1 and population 2. So that's 1 t-test. This will be the null hypothesis for that. I would have to do the null hypothesis or the t-test for the comparison of mu2 and mu3. Right? And then there's one more, because I don't know if I'm going to reject these or not, right? So I don't know that mu1 equals mu2 and mu2 equals mu3. So I can also test whether mu1 equals mu3. And so I could do 3 separate 2 sample t-tests in order to test that null hypothesis there. All right? That will be our only option given what we know. All right? And so what we're doing here, using these 3 separate t-tests, we're using multiple tests, all right? And basically what we're doing is we're conducting what statisticians call multiple comparisons. All right. Now, what you'll find is that statisticians don't like multiple comparisons. We can do them, but we have to do some extra stuff in order to do them, because there is an issue. Doing multiple comparisons actually increase our type 1 error rate. It increases the type 1 error rate. Now, we just had an exam on chapters 6 through 8, so you guys should know the answer to this question. What variable did we use for the type 1 error rate?
Alpha?
It was alpha. Good job, right? So our type 1 error rate, that's alpha, right? We also call that our significance level. And we also said that it is a probability, right? It's the probability of rejecting the null when we actually shouldn't. That means the null hypothesis is true. All right? So when we conduct multiple t-tests up here, this type 1 error rate that we as the researcher gets to set, it gets inflated. It's actually bigger than what we state. All right? And so we have this chart here that tells us, all right, depending on your number of groups, if you set your type 1 error rate at 0.05, that's the most commonly used type 1 error rate, then your actual type 1 error rate is going to increase, right? So notice here, this is an I again. I represents your number of groups. Number of groups, right? So when we have 2 groups, we're only going to do 1 t-test, right? So our type 1 error rate is actually the 0.05 that we set. But if we have 3 groups, we're going to have 3 separate t-tests that we're going to do, which means our type 1 error rate is no longer 0.05, it's actually 0.12, all right? Because we're doing multiple tests, so it's going to increase the type 1 error rate. Notice here, if I have 4 different groups, I'm going to do approximately 6. I'm going to do 6 hypothesis tests if I use the 2-sample t-test. Notice here, that type 1 error rate is no longer 0.05, it's 0.20, all right? And so we don't want such high type 1 error rates, right? If we set it at 0.05, we want to keep it at 0.5 and not these numbers here. And so to keep the type 1 error rate as we expect it to be, we need a new method instead of doing these multiple comparisons with these multiple t-tests. And so that method is known as the analysis of variance. All right? And the abbreviation for analysis of variance is ANOVA. All right? So we'll use one single method known as the analysis of variance, or the ANOVA method, in order to just do one test instead of multiple t-tests. And that way we can keep our type 1 error rate the same, because we don't want to have high probabilities of making an error. Okay? So, let's talk about the analysis of variance. There's actually multiple ANOVAs that we can conduct. We're just going to look at the simplest one. It is called the one-way ANOVA. The one-way analysis of variance. We call it one-way because we have one grouping variable. There are some studies where you may have 2 grouping variables. We call that a two-way ANOVA, all right? Now, this is an extension of your 2-sample t-test. There is another extension of your dependent samples t-test. We're not going to look at that. and we call that a repeated measures ANOVA. So those of you who major in like biology, you'll probably look at all of those, right? Or if you're gonna do biostatistics or something like that. But this one way ANOVA is the only one that we're gonna look at. Sometimes this one grouping variable we call a factor. So some people may, or if you go online and you use notes online to study, some people might call this the one factor ANOVA. Most places use one way ANOVA. But there's a two factor ANOVA, so on and so forth. For this, remember I is our number of groups. Capital I. And so our null hypothesis for this is always going to be that all of the means are going to be equal, right? And we stop at the number of groups. Our alternative hypothesis is that not all means are equal. Some people say at least one mean is not equal. All right, and they say, notice here I use a mu with a subscript I, lowercase I, where it can be one of those means depending on the number of means we have. So at least one of the means is not equal. All right. Now, this null hypothesis is not as simple as all the others we dealt with, right? The two sample t-test, mu1 equals mu2. That's one claim, right? mu1 equals mu2. When we had the pair sample t-test, mu sub d equals 0. That was one claim, one statement, right? Well, here, when I have all of these means being equal to each other, we have multiple claims here, right? So when I have H naught, mu1 equals mu2 equals mu3, I'm saying that mu1 equals mu2, mu2 equals mu3, and I'm saying mu1 equals mu3, all right? I'm making three separate claims with that one null hypothesis, all right? So instead of that being a regular null hypothesis, we start to call these compound null hypotheses, all right? Like a compound sentence has more than one statement, right? So we have a compound null hypothesis. Well, something about these compound null hypotheses is that the alternative hypothesis is inherently non-directional, all right? That means we're never going to have a directional alternative hypothesis for these tests here. All right? Our alternative is always going to be that not all of these are equal. All right? So one thing to remember, all alternatives are non-directional whenever we have compound null hypotheses. We're going to see other tests that are compound, that have compound null hypotheses. So if we reject null, the test does not yield a directional conclusion. All it's going to say that the null hypothesis is different. The means are different. But there are some multiple comparison methods that you can do to make some directional claims. But that's after you conduct this test. So if you look in your textbook, there's a whole section called multiple comparisons. We're not going to look at that in this course. But you can read it. You have the textbook. All right? If you wanted to make directional claims. Now, to conduct this hypothesis test, we're going to actually look at variability. Notice the name analysis of variance, right? So we're doing a hypothesis test about population means, but we're going to analyze variance in order to help us get to a conclusion. There are two types of variance. There's your between group variance or variability, and there's within group variability. All right. So every time I want to compare more than two means and I'm doing an analysis of variance, I'm going to look at two sources of variance: between group, within group. All right. The between group variability is related to the variance of the group sample means, right? So I'm going to go to all of my sample means: y bar 1, y bar 2, y bar I, and I'm going to look at how spread out basically those group means are. That gives me a measure of the between group variability, right? If I go to my sample data and one of those means is much different than the other, then that variance is going to be high. I have evidence against my null hypothesis, okay? But sometimes the variability within the group can kind of get in the way of us seeing some of those between group differences. So we also have to look at within group variability. That's related to the variance or how spread out each of the observations in your data set are. And so one way to say that is the sample variance of the observations within each group. So if I go to group 1, what's the variance? How spread out are the observations in that group? If it's large, all right, it may hurt me from seeing my between group variability. And I'll do that for every group. If it's small, I'll be able to see my between group variability very well. And so there's going to be some formulas and stuff that I'm about to go over that I won't ask you specifically to use these to do calculations, but we always think that we should let you know about the concepts behind these things, right? And so if you don't fully understand everything, it's okay. All right? So I'm going to go through 3 scenarios here and talk about between group variability and within group variability, right? Because that's the mathematics behind the ANOVA. So in this first example, we have 3 groups, and we simulated this data so that our null hypothesis is true, right? Here I have 4 groups, 1, 2, 3, 4. And my null hypothesis is true. That means all of these population means that created this sample data, all of them are equal. Now I have dot plots here that are vertical, right? And so all of my data, my sample data from our collected sample for group 1 is given here. Group 2 is given here. That data is given by that second dot plot. Group 3 is here, and group 4 is here, right? The horizontal line segment within each of those groups, that's your Y bar. So notice these values range from a little below 31 to almost 34 in group 1, right? From 31 to 34, those are the values. And the sample mean for that group is a little over 32. I'm going to call that Y bar sub 1. All right. For group 2, it has the same spread or a very similar spread. The smallest value in this data set is a little below 31 and then above 33 with a sample mean Y bar sub 2 of that value there, which is close to 32, right? And I can do that for all of these groups here. Our third sample mean is a little below 32. So that's Y bar sub 3. And here I have Y bar sub 4. So when I talk about within group variability, I'm talking about how spread out our observations are within each of these groups, right? And that's given by the distance from here to here for that first group relative to the mean. The same thing from here to here for the second group relative to the mean, so on and so forth, right? So our within group variability is pretty small, right? Our values range from about 31 to 34. Values from 31 to 34 are pretty small in value. This equation here gives us a measure of our within group variability. It's not focusing on the range, it's focusing on the sample variance. Here I have my sample variance. Remember from chapter 2, we talked about sample standard deviation and variance. Variance was S squared. All right. So I'm going to go to each group, and I'm going to multiply n minus 1 variance, add them all up. That gives me my within group variability. All right. When I talk about between group variability, here's some additional notation here. Let's look at this whole statement here. This is a between group variability measure. It has your group sample mean. And we hadn't talked about y with a double bar atop of it, y bar. That is actually your grand mean. So that's the overall mean of your data set. So what we can do is look at the mean of group 1, mean of group 2, mean of group 3, mean of group 4 separately. Those are your group sample means. And if we subtract those values from the overall mean, your grand mean, so assume that all of your data, just look at all of your data at once instead of separately and calculate the mean, that is your grand mean. So this, if I do that, gives us how much variability we have between these means here, right? And as we can see, y bar 1 is close in value to y bar 2. That's close in value to y bar 3. That's close in value to y bar 4, right? And so in this case, our between group variability is also small across our groups. All right? In a scenario like this provides strong evidence that H naught is true. All right? All of our y bars are almost equal in value, so our between group variance is small. And then with all of these separate groups, the spread is very similar and also small. That's evidence that our null hypothesis is true. We will probably fail to reject in this case. All right, so that's one case here. I'm going to look at another case here. In this case, we created this scatter plot or this dot plot or grouped dot plot with the assumption that the mean for group 1 in the population is equal to the mean of group 2. Here we have y bar 1 and y bar 2. They're almost equal in value, right? So it makes sense. So this is y bar 1, this is y bar 2. All right, we also simulated this, so y bar 3 would be equal to, mu 3 would be equal to mu 4. And in our sample, we see y bar 3 pretty close in value compared to y bar 4. But if you notice, y bar 1 and y bar 2 are much different compared to y bar 3 and y bar 4, right? And so this would be a case where if I were to look at my between group variability, right? And I got to look at all 4 groups. Since y bar 3 is different from y bar 2 and y bar 4 is different from y bar 2, so on and so forth, our between group variability, especially compared to the other example, our between group variability is going to be pretty large across our groups because we have spread much more than we had in the last example. All right? So my between group variability is large across groups. But if you look at the individual groups, they all have a small and a very similar spread about their sample means, right? This one goes from like 29 to 31, a little below 29 to a little below 31, right? The spread within that group is pretty small. The same thing happens with these groups here. So our within group variability is small within each group, right? And so this is evidence against the null. Mu1 equals mu2 equals mu3 equals mu4. So if I ever get in a case where the between group variability is large, especially compared to the within group variability being small, I'm going to have evidence against my null hypothesis. Okay? So again, this is why we're looking at variances here instead of looking at means just by themselves. Now, there are cases where we may not have very strong evidence, or some things may block us from really seeing whether we should reject or fail to reject. And so I have another case of data where my null hypothesis is false. So I generated this data, or our textbook generated this data, so that our null hypothesis is false. Remember, our null hypothesis, mu1 equals mu2 equals mu3 equals mu4 is false. That's how we generated this data set. Now, what you're going to notice different about this graph, I'm going to go up to the previous graph. Notice the y-axis here. This y-axis ran from 29 to 34. That's why I say our variability within group is small. In this previous example, again, 29 to 34, our variability within the group is small. The spread within each group is small. Now, if I look at this last graph here, it's going from 10 to 60. That's how we've labeled our axis, right? So we have a lot of variability. And I want you guys to tell me what type of variability is large in this case. Okay. Caroline? Would the within group or the between group variability be large in this case?
Between?
Okay, between. What do you say? Between? Aaron? Okay. Lydia? Between? Okay. What do you say? What do you say? Okay. What do you say? I get it within. 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 And I would agree. The within group variability is large, right? Because when we look within the group, right, think about covering up all of this other stuff. You can't see, right? But I'm looking at the variability in this group. Think about how spread out those values are, especially compared to the previous example. We're going from a below 10 to above 50, right? I have a lot of spread within this group. I have a lot of spread within this group, right? I have a lot of spread within this group, and of course, a lot of spread within that group, right? That's within group variability. All right, so our within group variability is large, but let's look within each group, right? When I look at, let's look between each group. When I'm talking about between group variability, I'm comparing these means that are given by these horizontal lines here, right? So y bar 1 is there. This is y bar 2, y bar 3, y bar 4. So does the between group variability appear to be large or small when I look at those means across group, right? Do they vary a lot Do they look similar in value? What do you say, Caroline?
Looks similar.
They look similar, right? What about 1 through 4? They look similar to her. Grace? Aaron? Everybody say similar? Right. So relative to the spread within group, our between group values do not appear to be very large across groups. But our null hypothesis is actually false in this case. All right? And so the point that I'm trying to make here is when our within group variability is large, it clouds our judgment from really being able to see that these means here are different. So they may be very different, they may not. We have to go through the actual test to see that. But this data was simulated so that the null hypothesis is false. So those means are in fact different. But again, when our within group variability is large, it's hard to see that. All right? So when the within group variability is large, it's difficult to see that mu1, mu2, mu3, and mu4 are not all equal. All right? So we don't like a lot of within group variability, especially compared to the between group variability. All right. So with that being said, right, we'll probably never ever see this type of graph again. Trying to walk you through while we're looking at variance, right? But this next comes to stuff that you really need to know. All right. It says ANOVA compares how variable the sample means are. That's that between group stuff, to how variable the observations are around each mean within group. So all throughout this chapter, I'm going to talk about between group and within group over and over again. All right. And basically, we get strong evidence against the null hypothesis when our between group variability is much greater than our within group variability. All right. That gives us the most evidence against our null hypothesis. Between group being much greater relative to the within group variability. All right. Now, in order for us to run an analysis of variance, we have to have certain requirements met. Now, I know when we were looking at the t-test, we focused on that normal distribution assumption. Well, depending on the number of groups we have to do that number of QQ plots and all that stuff. So we're going to kind of skip over that in this chapter. But these are the requirements in addition to normality. Our samples need to be regarded as random samples. So we always need random sampling. Otherwise, sampling distribution of your sample mean doesn't make sense. We need all of the observations within each group to be independent and normally distributed. And we have this extra requirement that all of the groups come from populations with the same variance. All right, if that's not the case, I can't make true comparisons. All right, so there are methods to check that. And then observations across groups are independent. Or we wouldn't be in the independent case. All right, so those are the assumptions or the requirements here. Let's talk about the ANOVA table. So again, these are going to be some formulas. The keywords I want you to know, right? So one of the keywords that I want you to know is sum of squares. The sum of squares is in every single ANOVA table, all right? In order to conduct the test of the equality of the means, we want to compare the variation between groups to the variation within groups. So what we're going to do, remember I said that this sum here gave us some information about between group variability. And this second sum gave us information about our within group variability. All right. Well, those two sums are called sum of squares. So we have sum of squares between, which is we will go to each group. I equals 1, lowercase I equals 1 capital I. We multiply the sample size times the deviation of each sample mean from the grand mean and square that. So it's like doing a standard deviation of your means. And at the end, they give you the value, what each of those symbols mean. All right? Our variation within groups is given from our sum of squares within. It's given by this sum here. So I go to each group, multiply the group sample size minus 1, which is the denominator of your sample variance formula, by the sample variance for that group. And that gives you your within group variability, and you add it up across groups. And then we have this more complicated sum here. It's kind of like a sum within a sum. We get the total sum of squares, all right? Our total sum of squares, you go to each group, so it says I from 1 to however number of groups you have. And every group I'm going to go to, I'm just going to do the difference of the individual observations. So almost every single dot on that previous dot plot. I subtract those from the grand mean and square it. And I basically get a formula for variance without the denominator. That's your total sum of squares. And one of the reasons why people like to use this is that we can decompose our total sum of squares using the following. Our sum of squares total equals our sum of squares between groups plus our sum of squares within groups. All right? So if I know the between, I know the within, I can get the total. Or if I know two of them, I can get the other. Now, these are not comparable measures, right? This and this, they're not comparable measures. And so in addition to having sum of squares in our analysis of variance, we have what we call mean squares. All right, and a mean squares is nothing more than a sum of squares divided by degrees of freedom, all right? So I'm going to take my sum of squares, and I'm going to divide by degrees of freedom, all right? So each of those sum of squares from above can be divided by degrees of freedom, and it takes the sample size into consideration so that we can have comparable measures of variability. Variability between groups and variability within groups, all right? Now, there's going to be some more formulas here, all right? These are our mean squares, all right? Our mean squares is our final measure of variation between groups. Instead of saying SS for sum of squares, we're going to have mean squares between. The mean squares is just your sum of squares between groups divided by the degrees of freedom for our group between group variability, which is I minus 1. So I take the group number of groups minus 1. That's our degrees of freedom between groups. All right. Our degrees of freedom within groups, all right, here's some more notation here, is N with a subscript of a dot. All right. That just means the total sample size across all groups. All right? That's the degrees of freedom. So I take the sum of squares within divided by the degrees of freedom within, which is that N with a subscript of a dot, your total sample size, minus I, that's an I there, which is your number of groups. All right? And so I can put all of this information together into one single table known as our ANOVA table, all right? And this is what I want you to be able to understand, right? So we have different sources of variability, right? We have variability between groups, variability within groups, and then we have our total, right? The degrees of freedom between groups is that I minus 4. So if I know the number of groups, subtract 1, I said 4. I minus 1, that is our degrees of freedom between groups. The degrees of freedom within groups is that n dot minus I. That's not a 1 there, that is an I, the number of groups. Every ANOVA table has our sum of squares, which is given by this formula here. And if you add these two sum of squares, you're going to get the total sum of squares. If you add these two degrees of freedom, you're going to get the total degrees of freedom, all right? And then the last column is nothing more than your mean squares, right? So if I take this sum of squares and divide it by its degrees of freedom, I get this mean square here. And the same thing happens over here, all right? And this table has actually another column. And you can think of 2 more columns, especially when we get to RStudio, but we won't get there until next class, all right? So we'll learn how to use this table to draw conclusions about whether all of the means are the same or at least one of those means are different. We'll do that next class. All right? I know that was a lot. All right. But if you don't remember anything, remember we're just going to use this table here and the relationships within that table. All right. Have a great day. Have a great weekend. I'll be having your grades done by Monday. All right. So have a good one. All right. Have a good day. You too.
We talked yesterday.
Okay, cool.
He speaks directly.
Uh-huh.
To be honest.
Yeah. So what did he say?
Actually, he don't know too much about biostatics.
Oh.
He says I should ask the PhD professor.
Oh, okay,
Yeah,
okay,
because
okay.
we don't have bachelor degree for.
Right, right. So should you major in stats or biology?
Yes, but he arranges some courses for me in the following semesters, and
Yeah.
contact an advisor to change my major.
Okay, okay.
Yeah.
So was one of those classes Calc 2?
Yeah, next semester.
Okay, good. Because I think if you take the Calc 2, does biology require Calc 2?
No.
Okay. Yeah. So that might be. Yeah. You need to talk to the advisor. But I'm thinking that I know some biostatisticians that come from statistics. You know what I mean? So some of the statistics PhD students in our department go on and they'll work in a department of biostatistics at a university. So they do research in biostatistics, right?
Yeah.
But yeah, you might want to talk to that. Yeah. Talk to the doctorate program over there in biostats.
Yes, he says the most important thing for me now is maintain a high GPA.
Yeah. Okay. Gotcha.